How well do you understand optimistic and pessimistic locking in your application code? Do you have second thoughts about them? How do you choose which one to use? Did you protect your application from concurrent edits, from deadlocks? There are no shortcuts to learning any of this. But there is one way you can help yourself to learn it better, to understand it better. The idea is very simple. No matter what programming language you use, no matter what libraries you use to access the database, whether you use ORMs or not, at the very bottom of all things, it's going to be SQL. It's going to be rows in the database. It's going to be locks and transactions, commits and rollbacks. If you can understand that, then suddenly you will be much more proficient when using any of these concepts from any database access library you use in your application code. I will show you the locks, the transactions, commits and rollbacks errors, deadlocks, concurrent edit errors. I will show you how you can design your code to recover from those, how you can write your code to never cause a deadlock. Here is the database schema which I will be using to demonstrate. It is my usual bookstore application. The table defining books with only the title, the table defining people with only the first and last name, those will be the book authors, and a junction table to join these two. One book can have multiple authors, one author can write multiple books. The detail in this junction table is the ordinal number of the author within the author list of one book. We will be updating that column. If you are a patron of my channel, you can download this database creation script from my Patreon page. So the technical request we will be dealing with is to take the authors of one book and then swap two adjacent authors, so to effectively move one author up in the list of the authors. That will include updating two rows in the database, and you can already see that there will be a lot of locking, interlocking, pending transactions, deadlocks and whatnot. I will not implement any transactions yet, which means that there will only be the implicit transactions imposed by the database itself. Let's implement this operation of swapping two adjacent authors. You can imagine writing an application code, and this would be very similar to what your library, your code will generate in SQL. I'm querying the book on design patterns. Let me query the database. Here it is, the four authors. Observe their ordinal numbers, 1, 2, 3, 4. The data are correct now. I will corrupt my database very soon, but this is what I want to see. This is the correct data. 1, 2, 3, 4 and the names. Anything other than this is a bug in my application. So let's start implementing that operation of moving one author up. There will be the parameter. I want to move author number 2 up, which means to swap authors number 2 and 1. Remember the book ID. I need the identity of the first person, the identity of the second person we're updating, and that ends the querying phase in this operation. Now we start thinking, calculating. I'm analyzing whether I have found both authors. I calculated the new values I want to write in the database. And then comes the writing phase, where I will update the row in the junction table to update the ordinal number of the specific author, and then update the second one as well, so I have updated 2 rows. What can go wrong? Well, multiple edits at the same time can go wrong. I will connect to the same database again with exactly the same script, but this time I will move the third author up, so to swap authors number 2 and 3. And there is one more detail. I want this second script to run concurrently with the first script. I will simulate concurrency using a dirty trick. I will add delay, 10 seconds delay to my first script right here before the updates. So you can imagine concurrent access to your database. Two users on the internet have clicked the exactly same button. The result is that two transactions, two large operations consisting of many queries, updates, deletes, whatever, are now happening at the same time, and they are fighting for access to the same database rows. That is concurrent access. That is what makes us devise such things as pessimistic and optimistic locking. In this particular situation, I will simulate concurrency this way. Look, I'm running the transactions. The first one is sleeping, but the second one has completed in the middle of it. Now the first one wakes up and runs to the end. Look what is the result. I'm not even going to read the names on the right. This is the problem I'm seeing. The ordinal numbers are garbled now. I have damaged the data in my database. That is why we need transactions to protect us from this. In relational database terms, we need isolation between these two concurrent operations so that we know that each of them will run to the end and produce correct, consistent data, even though there are other operations trying to modify those same data. These were the implicit transactions. What is the implicit transaction? If you do a select like this one, the database will run it inside a transaction. It means that while this select executes, no other update could change the data you're selecting here. So technically, each of these small statements alone is safe. But if you have multiple statements one after another, those multiple statements are not safe because other statements might execute in between them. So enter pessimistic locking, the first demo where we will use our own transactions to isolate the two large operations, each consisting of multiple statements. Before that, I have some coupons to share with you for video courses on DomeTrain. DomeTrain is an online courses platform run by fellow content creator Nick Chapsas, and it is the go-to place for up-to-date courses on modern software engineering topics. From testing to clean architecture and modular monoliths all the way to DDD, microservices, Docker and Kubernetes, DomeTrain has a rich collection of courses that will help you get up to speed with each topic by expert authors who have been practicing what they teach in real companies for years. DomeTrain just launched DomeTrain Pro, a subscription offering that gives access to all of the platform's courses. With more than 24,000 satisfied students, you can't go wrong with DomeTrain. And the first 100 of you can use code Zoran to get 15% off any course. I hope you will enjoy watching those video courses and that you will learn a lot about programming. Now back to my demo. Pessimistic locking begins by beginning a transaction. So I am pessimistic about the situation in which my script is running. I fear that there will be others trying to change my data. So I put my entire script into a begin transaction and commit transaction block so that nobody can touch anything I am currently working with. My transaction will be isolated from others, but I should also set the transaction isolation level. I will choose the most restrictive one, serializable, so nobody can touch anything I'm working with right now. Looking from the outside, it will be as if everybody else were serialized. That means they came after my entire transaction. These are actually two statements. Begin transaction is one statement, set transaction isolation level is the other one. I'm just saving vertical space. Oh, this looks so ugly. You should put these on 2 lines of code. Then there goes the entire script, and at the very end, when everything is over, I just commit the transaction. I will be running this script twice again. Run one, run the second in parallel. And look, the second script is now blocked, waiting for the first transaction to commit, and only then can it continue with whatever it wanted to do. But something is wrong. Something is wrong here. The error says that my first transaction was deadlocked, and the database has chosen that transaction as the deadlock victim. It has terminated that one and left the other one to complete. So from the data, I can see that the second script has indeed swapped authors number 3 and 2, that is Richard Helm and Ralph Johnson, but the first one was killed. I believe this requires some explanation, and it is about locking. You can imagine this initial state of the data and what the first transaction did before it encountered that wait instruction. It has read Erich Gamma and Richard Helm. And you can imagine, now this is the principal explanation I'm giving you. You can imagine it putting the read lock on both rows. Different databases implement locking in slightly different ways. See my explanation here as a principal schema about how that works. You can imagine one transaction saying, "This I'm reading." Everybody else can read it, but nobody can write it until I commit. Only in that way, my first transaction will know for certain that when it starts updating data based on what it read, it will be right about that. Nobody else has changed the data, causing a bug in my script, in my transaction. That is where the second transaction begins, and it also reads rows, this time Richard Helm and Ralph Johnson, and puts read locks onto them. You can see that Richard Helm has 2 read locks at the same time. That is perfectly legal. You can read as many times as you want in parallel, but you cannot write if anybody else is reading that. The second transaction then goes to update these 2 rows. It attempts to update the third author first, that is Ralph Johnson. So it acquires the right lock. It says, I'm going to update these data. Let me do that. And the database is happy. It says, okay, go write. You're the only one who was reading it. Then it attempts to upgrade the read lock to read write lock on the second author, Richard Helm. And the problems happen there. The database would say, no, there's somebody else reading this, you must wait until that one commits. That is where serializable isolation level comes to play, because the first transaction was the first one to say, I'm working with these data, and the second transaction only came later, and so it must be serialized after the first transaction commits. Therefore, it must go to sleep. The first transaction wakes up and says, okay, now I want to update Richard Helm to change his ordinal number, but alas, it also encounters the read lock from somebody else. And that is the resource where the 2 transactions deadlock. They wait for each other. That is the consequence of pessimistic locking. Nothing bad has happened to data, but something bad has happened to the application. How do we solve this problem, the deadlock problem? There is one general solution to deadlocks. It is based on the idea that you could imagine your entire database as a number of rows, as a bunch of rows, and then you can sort all those rows and all those tables into one global sort order. For example, you can imagine that the book with a larger ID comes after the book with a smaller ID. You can imagine that the outer with the larger ordinal number comes after the outer with the smaller ordinal number. Since I am updating outer's ordinal numbers in my operation, I can explicitly place an update lock on the outer with the smaller ordinal number first. Then cut this select, put it later, and then acquire the update lock on the outer with the larger ordinal number. So I will always lock outers in the growing order of ordinal numbers, and there will never be that inversion. I'm waiting for the larger, he's waiting for the smaller, and now we're deadlocked. That will never happen. Alternatively, if you are practicing DDD, or even if you're not, if you're using aggregates, you can only lock the aggregate root. And so everything that happens inside one aggregate will be yours. There will be no two concurrent transactions on a single aggregate. I think this is a much better idea. Anyway, two transactions again running in parallel, running one, running two. The two is blocked, waiting for the first one to complete. Now the first one will complete, and it will complete first. Unlocking the resources the second transaction was waiting for, and the second transaction will now complete. Everybody will commit. So the end result, as you can see, is that Erich Gamma and Richard Helm have swapped their positions first, and then the second transaction took over, swapping Erich Gamma and Ralph Johnson. That is exactly what I would expect to happen. And this is what is good with pessimistic locking. I really feel safe this way. The downside of pessimistic locking is performance. The transaction will be long. Everything, the entire script is one transaction. It means that there will be a lot of locks in the database. That makes the database generally slower, especially if multiple concurrent operations are reading the same rows in the database. You might start noticing the drop in performance. I will advise you, especially while your project is small, to start with pessimistic locking, and when you notice contingency, then to consider something more optimized. And that more optimized is optimistic transactions. Again, if you are a sponsor of my channel, you can download all this code from my Patreon page. If you're not the sponsor, please become one. Running a channel like this one is an expensive exercise, and I'm really grateful to everyone who is helping me with that. Visit me on Patreon and become a sponsor. That will give you access to all the source code from more than 100 videos I have on my channel so far. That will give you access to the upcoming video course I'm working on at Udemy. You can also visit me on my Discord server, where you can take part in discussions about C# and dotnet. Now, the optimistic transactions. Optimistic locking comes from realizing that our typical operation on the database consists of three parts. One is to gather the data from the database through select queries. After that, we might be thinking, calculating, doing stuff in memory, deciding what to do. And then comes the third phase, writing the data back into the database. The optimistic means that we hope that there will be nobody jumping in between these phases. So before I start updating these rows, I hope nobody has already changed them, making the results of select queries inaccurate. But I cannot know that. And so we take precautions. Every update, every delete must include a filter where whatever I was testing and the row version did not change since I read it. Then I check the row count, which tells how many rows this update has updated, and if it was 0, it means that the row version has changed. Somebody was writing into this very row while I was not looking, and I must fail. I cannot progress any further from this point. Since there are 2 updates, I will still execute them within the transaction, because it could happen that the first one passes and the second one fails. I must roll back the first one, so there will still be a pessimistic transaction here, but a very short one compared to what I had before. How do we implement those row versions? How do we implement versioning? That depends on the database you're using. Invariably, there will be some row version column in the table on which you want to use optimistic locking. In SQL Server, the type of this column is row version. It is an auto-increment 8-byte number that is unique for the database. Every time you do a write on the database, this counter increments by 1. And so you can just see, let's say it a timestamp, but it has nothing to do with time, the timestamp of the last change to this row. Oracle will use what they call SCN, System Change Number. It is also an incrementing number, which is incremented on every commit. A very similar idea to what SQL Server does. In Postgres, you would use probably transaction ID, which is also an incrementing number. So the idea is very simple in all cases. You need to read the documentation for your database and use whatever that database uses. You will be safe. The idea is that now I have a value in every row that indicates the last time of the change made to that row. As the database was adding values to this newly added column, it was effectively changing each column, and this counter was increasing. So you can see that every row in the book authors table, which I want to protect with optimistic locks, now has a unique number indicating the time when it was last changed. Let's implement those optimistic locks then. This is the idea. When you select the data before updating them, you read whatever you need of the data, but also read the row version and remember it. That is the row version which you saw. Then comes the update. And I say update for this book ID, this person ID, but also this row version. If anybody has touched this row for writing in the meanwhile, there was no transaction in the meanwhile, so it was writable. If anybody did write into my column, the row version would not match, and the update would effectively produce no change at all. So I will count how many rows I have updated by adding one row count, the other row count to the counter, and then at the very end, when everything ends, I expect 2 rows to be changed. If it's not 2, something is wrong, and I must roll back the transaction and I must rise the error. Otherwise, if there were 2 updates, I will just commit the transaction. I'm happy. That is the optimistic transaction, the optimistic locking. I am optimistic that nothing will happen. And if the row count was 2, really nothing bad happened and I can commit my transaction. You see, I'm smiling. I'm really optimistic about this one. Let me run it. Running 1, running 2. The second transaction ended immediately because it doesn't have to wait for anyone. But look at the results of the first transaction. I see no change here. What's happening? I'll show you what's happening. There's something written in blood here. Concurrent edit. That's my custom error. I have raised that. How did this happen? It should be clear by now. You have seen all the explanations and you have seen how pessimistic locking works. The second transaction updates the author number 3 happily. The row version is the same as it saw, but now it is updated. Then it updates the author number 2, and that includes updating its row version, and it commits. The transaction number 1 wakes up. There are no locks in the database. It can quickly get to updating the author number 2, but alas, the row version is not the same what it saw before beginning the transaction. And so all it can do is roll back and raise the error. That is optimistic locking. How optimistic can it be when it failed? Well, this is the point. You really hope, and you are optimistic about that there will be no concurrent edits on the very same rows. You hope for that. And very often you will be right. Very often when there is contingency on the tables, you will be right that many concurrent transactions will update the rows in the table, but not exactly the same rows. That's the point. That is how optimistic locking makes your database effectively faster when there are many concurrent transactions on it. However, a certain number of errors will happen. And what do you do when you encounter the concurrent update error? There are generally 2 approaches to that. One is to bubble it up to the user if there is a human user, and to say, somebody else is changing the same thing. Now, read what they did. You have seen that my transaction has seen the state as the second transaction left it. So I can read the entire state again and present it to the user. And then let the user decide whether they want to repeat the operation or change something and try again. That is the human decision. The second possibility is that you design your operations in such a way that they are repeatable. Repeatable once. I know that it failed, so there's no change in the database, but I know that it's just swapping authors number 2 and 1. Let's do it again. Well, good. This time I was the only one to change those 2 rows. There was no concurrent added this time and the operation succeeded. Everything works fine in the end. It's only the difference in the ways you recover from errors. Now get back to your application code, get back to your libraries, to your ORMs, and see how they generate all this code, all these begin, transaction, commit, rollback, everything. I hope you will have no second thoughts now about how your transactions are working in the database.